So I'll record office hours and put these up as soon as I can before tomorrow. We're doing number 5, 4x squared plus 9y squared equals 36. You want your equation of the ellipse to equal 1. So divide everything by whatever constant you have. So you'll have x squared over 9 plus y squared over 4 equals 1. And so if you look at it in terms of these squares, it looks a lot like a circle. It's a sum of squares. We're just stretching the axes a little bit different. So we saw examples of in class, if we wanted to come up with a parameterization, you could say something like x is 3 cosine of theta and y is 2 sine theta. So that way it'll satisfy this equation x over 3 squared plus y over 2 squared equals 1. So, right, if we just plug those in for the x's and y's, that'll give us a valid statement, which will give us means this is a correct parameterization. But you don't quite need that. You could just plug in points. In Cartesian coordinates. So for example, if x is 0, what's our y value going to be? So we'd have y over 2 squared equals 1. So that means y over 2 is plus or minus 1. So y has to be plus or minus 2. Do the same thing for your y's. If y is 0, if we're on the x-axis, you should be able to find x has to be plus or minus 3. So we get an ellipse. And it should be fairly clear that the major axis. Do they want the length? Yeah, so the major axis length. Minor axis going to be 4. So the length of the major axis and the length of the minor axis. And then I don't think there's much else to do. Since we're not, the foci would be, you have to follow a formula. The foci are going to be somewhere here, but if we're not asking for that, you don't really have to find it.
What about the vertices?
Yeah, so the vertices are going to be along the major axes. So your vertices are here. So your vertices are minus 3, 0 and 3, 0. So vertices are just the points, the endpoints of the major axes. We go.
Are we still working on the ellipse question, or can we ask more questions?
We can move on. I think most people got it.
Okay. I had a question on one of the written exams, or sorry, the practice exams. So maybe it's probably just gonna be quick, but for this one, for 1B, I sort of used integration by parts to find the integral of that, and then did that to infinity. But when I do that, it doesn't end up getting the answer that the key provides, and I'm just confused why. So maybe we could walk through that problem.
Yeah. So we'll check. You should get a finite value. So you want to do integration by parts. Your u is going to be your x, your dv, e to the minus 2x. So du gives us dx. And then v, when we integrate that, minus 1/2 e to the minus 2x. So our integral now becomes minus 1/2 e to the minus 2x. We got to evaluate that guy from 0 to infinity minus the integral of v du. So that minus 1/2, we'll change that sign. And then we'll have an e to the minus 2x dx. finishing the integral, so minus 1/2 x e to the minus 2x. I like to just do all of the evaluations at the end. You could do the evaluations now for that part if you wanted. And then when we integrate again, we'll have another factor of negative 1/2. So to evaluate it, we can compute everything as a limit. Here, let's just do all the evaluations at the end. So evaluate your t, evaluate your 0. And now compute the limit.
So if you find like the integral of the whole thing like first, and then you put in 0 to infinity, it ends up like, can I kind of write out what I'm saying?
Sure.
Okay, so if you sort and I maybe you just can't do this, but um, when I don't know if it'll let me write. I guess I can do it like this.
So the integral of everything should have been minus 1/2 x e to the minus 2x minus 1/4 e to the minus 2x.
Okay. Maybe I got something similar to that. It just maybe I just did something wrong. I don't know.
Try to check it. So compute a derivative. If we compute a derivative of this guy, do we get back x e to the negative 2x?
Can I ask a quick question?
I guess if we wanted to finish this, you got to make sure to show that these limits both go to 0. So your answer should be 1/4. Sure, go ahead. So what's the other question?
Can I share screen real quick?
Yeah, go for it.
So can you please help me with this 5b, the Taylor remainder formula question?
Yeah, what's this from? Spring 2021?
Yeah.
So our nth derivative, find a Maclaurin series, fairly straightforward. Suppose that T3 is the third degree Taylor polynomial centered at 0 is used to estimate f of 1/2. Use the Taylor formula, the error bound, to approximate or to find the error. Okay. And I didn't write it down, but we were using the third Taylor polynomial. So the error formula is going to be absolute value of the fourth derivative. I guess we should say the error bound for the third Taylor polynomial. What did they say the center of the Taylor polynomial was at? Was it at 0?
Yeah, the set is centered at 0. Yeah.
Okay, so it's going to be x minus 0 to the fourth. So this is similar to one we were looking at in class today, but phrased a little bit differently. The one in class, we were actually given a range of values for x and asked to show what was the maximum error within that range. In this case, we are actually given the x value that we were computing and approximating. So we know the x value is going to be 1/2. We simply need to choose the z value. So let's go ahead and fill in this f to the fourth, or the fourth derivative, in regards to z. So we'll have a 3 factorial over 3 minus 2x to the 4. We'll have a 4 factorial from that piece. And we're going to have an x to the fourth, which we should just put as 1/2 to the fourth. And I forgot to put in the 1/2 here for that value of x as well. Oh, wait a minute. Sorry. That should be our z, since we want fn of z. Let me rewrite that. So minus 2 to the fourth, 3 factorial over 3 minus 2. Z is our specially chosen z value. So that z isn't necessarily 1/2. Could be, though. And so we want to find z in between 0 and 1/2. So it's always between the center of the Taylor series and whatever x value we chose. And we want to maximize that expression. So let's simplify things a little bit. 3 factorial and 4 factorial is going to give us a factor of 4 in the denominator. The minus sign doesn't matter because we're going to have an absolute value. 2 to the fourth and 1/2 to the fourth are going to cancel as well. So we're going to be left with 1 over 3 minus 2z to the fourth. And we want to maximize this. So if z is between 0 and 1/2, how do we maximize this expression? Usually good to check the endpoints. What happens if z is 0? Z is 0, we will have a 3 to the fourth in the denominator. So 1 over 4 times 3 to the fourth. If z is equal to 1/2, then it'll be 3 minus 1, so it'll be a 2 to the 1/4 in the denominator. So we want to choose that endpoint. So our error bound is 1 over 64.
Makes sense. Thank you very much.
When we could just do an example so I could see where I'm going wrong.
Let's take a look. Are there any? Let's take a look on final review. Dishwasher method. Let's go down.
There's a whole bunch on like the new WebAssign that we got that's due tonight too, if we can't find any on the.
Sure, let's take a look at one of these. Because there wasn't any on the review. I don't want to fish through any of the old exams. The other thing, we could either check the WebAssign or the book. Book problems should be the same as WebAssign though, up to changing constants. So here's one. Your numbers might be a little different. So area inside the first curve. And outside the second. So the first curve they give is 13 cosine theta. Second curve, 6 plus cosine theta. So you want to graph them. So 13 cosine theta. Radius is going to start out at 13. And then it's going to have, there's going to be a circle. So we've graphed these in class. Should know, be able to recognize the graphs of like r cosine theta. R is equal to cosine theta, or r is equal to sine theta times some scalar multiple. Going to be circles. Six plus cosine theta is going to be a little weird. So if we make a table, first value is going to be 7. Pi over 4, 6 plus root 2 over 2. Pi over 2, give us 6. 3 pi over 4 will give us 6 minus root 2 over 2. And then at pi, it'll give us 5. So you should recognize these by the diagram that we sent out yesterday. Anytime it's like a constant plus sine theta or a constant plus sine theta, cosine theta, or if there's a multiple here, it's going to look like a cardioid or one of these limmason. So you kind of just have to determine how much of a hump there is, or if it's a cusp, if it turns into a loop. So if we plot it at 7, maybe somewhere there, then at pi over 2, we go up to 6. And so it's going to come maybe there. 3 pi over 4, and then pi. It'll be maybe at 5. And then what's going to happen as we keep going around the circle, at 5 pi over 4, we're going to be at 6 minus square root of 2 over 2. And so it's going to like repeat. So one thing to note, root 2 over 2, again, it's about 0.75. So this 6 minus root 2 over 2 is going to be like 5.5, 5.25. So the radius is actually going to be bigger, and then it's going to shrink down at 5. So it's going to be a slight little hump here. As it comes around. So our graph looks kind of like that. And now what do we want? So we want inside first curve, outside the second. So inside the first curve, inside the circle, And outside the second is going to give us this area here. So what we need to do is find these intersection points. And moreover, we want to find them in like a continuous range. So it'll probably start at a negative theta. And then as we go around, positive theta to there. So you want to just set those equal to each other to find those thetas. And with the numbers they give us, it's not going to be nice. I think there was one like this on your written homework as well, where the numbers don't work out too nice. But don't worry too much about how bad the numbers are. Actually, no, these ones will work out just fine. Sorry. Since you don't actually have to be able to compute the precise angles, you really just need to understand the trig ratios. But I guess in this case, we'll have 12 cosine theta equals 6. So cosine theta equals 1/2. So if you get harder numbers in a situation like this, I think on one of the homework problems, it was like theta is arc sine of 1/4 or something like that. Really, all you have to understand is that the intersection points are going to be such that, here, let me put it in a different color actually. These intersection points corresponds to angles where the cosine ratio is 1/2. And so you can figure out the third side if you have to when we're evaluating our sines and cosines. So cosine theta equals 1/2. You'll be able to find those negative pi over 3 and pi over 3. But again, if we can actually compute and find theta, knowing the cosine ratio and which quadrants they're in will be enough to help us solve the end result and compute the remaining trig. Namely, so now we want to set up our integral between theta 1 to theta 2. And it's always going to be the outside minus the inside d theta. So our outside was 13 cosine theta minus 6 plus cosine theta d theta. And so what do we get? 12 cosine theta minus 60 theta. Fairly easy integral from there. So now when we're evaluating these guys on sine, you can list the angles if you want. That's pretty nice. When we actually have to plug them in here, it's going to be a little difficult, since if you have to define the angles in terms of arc trig functions, you will have to take the difference of those. But the difference shouldn't be too bad. You should usually be able to find the difference because they usually differ by, like, one might be theta, the other one might be pi minus theta or something to that effect. So use your trig and your geometry nicely enough, at least on WebAssign, since we have pi over 3 and negative pi over 3. We can compute the sine. So sine of pi over 3 is going to be root 3 over 2. And then, so what are we left with? I think the 6's cancel off, yeah? Oh no, they double. All the terms double. So we've got 6 root 3 plus another 6 root 3. So 12 root 3. And then we will have 2 pi and 2 pi. Sorry, minus 4 pi.
Thank you, sir.
Is anyone next to ask a question? Or like, can I ask one?
I was gonna ask a quick one, but if you want to go first, you can.
No, you got it.
Okay. I just need help on the number one written homework. I'm not too sure on what it's asking. Because I think I know how to do it, but I don't know exactly quite what it wants.
Ah, yeah.
It's probably something it doesn't think. Because pretty sure you just take the derivatives and then find the 0 points and that's it, but I didn't think that was.
No, that's the gist of it. I think we kind of mentioned this. We did problems like this in class, but I don't know if we had time to work through all of them. I kind of mentioned how to do them, but we didn't really see too many examples. You just have to think, since we're parameterizing the coordinates independently, x of t and y of t, x of t models the rate of change in the x direction, or the position in the x direction. And so you kind of have to think, well, in terms of how the particle is moving, there's going to be one leftmost point, and moreover, it's going to be particles moving left, moving left, moving left, and it's going to stop and start moving right.
Right.
So how does that correspond to derivatives? Think back.
Because I know the first derivative is usually interpreted as the slope, and then the second one is interpreted as the x and y. Well, not x and y, but the interception points, or how the. No, actually, I'm gonna correct myself on that. It's how the function changes, I guess. Like when it goes up, concaves up and concaves down.
Right. So first derivative measures rate of change, meaning if I'm moving in the left direction, moving in the left, then all of a sudden stop and move back to the right, what's happening at that point in terms of the rate of change on x?
Changing positions. So it's kind of similar to like concave up or down, how it reaches its minimum or max and it changes.
Well, I mean, yeah, there's no concavity that we actually need. It means that the first derivative.
No, that's just what I see it as.
The first derivative at the leftmost point has to be 0. In other words, of x. So dx dt over here has to be 0. The other thing you can kind of think about is if we drew the tangent line right here at the leftmost point, it'd be vertical. So vertical tangent line means that the rate of change of x is 0.
Right.
Right. The slope of the tangent line is 0, or is infinity. So the rate of change of x is 0. Similarly for y, the bottommost point dy dt has to be 0.
So you just find the first derivative, sum the 0, and then solve from there.
Yep.
See, I thought this was a lot harder than I thought. Okay, well, that kind of makes more sense. Let me mess around with that, and then I'll ask if I have questions. Thank you.
Welcome.
I have a question kind of about the problem that I was confused about before. I think I'm not like remembering the process correctly. So I don't know if you remember which one that was, but it was problem, I think 1B on the exam, the final exam, summer 2020.
Yeah.
So when I did the integral out and I checked that I had the right integral with the integral calculator, I got like negative 2x minus 1 over 4e to the 2x. And then, so when you plug in the bounds from 0 to infinity for that, you just do the limit as that goes to infinity, right?
For the upper
Minus,
bound.
yeah. And then minus, okay. I don't know what I'm doing wrong then, because
So I would be careful using things like integral calculator and all that, because they will spit out erroneous answers, or at least answers that are not quite in the nicest of forms.
yeah, I just checked it with the one I did, and I'm just confused because it like the one it kind of spit out was also what I got pretty much almost exactly as my integral, and it kind of confirmed what I was. I'm just kind of confused why it doesn't work.
It should work. You're getting the same thing. It sounds like you're just computing your limits. Maybe a little weird.
Yeah. Because can I like share a whiteboard and just show what I got?
Sure, if you want.
Okay, so what I got was like negative 2x plus 1 over 4e to the 2x, and I checked and this was correct.
Yep.
And then, so when you plug in 0 to like infinity, it would just be like the limit as that goes to infinity, which I'm just confused like why that's not infinity.
Well, so the numerator will give you infinity, and the denominator will also give you infinity.
Right. And so I did the like L'Hopital.
Yep.
And got 2 over 4, and then I guess it'd be, yeah, 2 over 4, or this, in this case, it'd be 8, sorry, 8, e to the 2x. And
Yep.
so wouldn't the bottom go to 0, or would you have to do like,
We're going to infinity, so the bottom goes to infinity.
yeah, so, but then wouldn't the whole thing go to 0?
Whole thing goes to 0, yeah.
So then why is it 1/4 is the correct answer?
So it's saying when we plug in the upper limit.
Oh, did I just forget to minus the 0?
Yeah.
Oh, okay, I understand now. Okay, cool. Sorry, that was super simple, but I couldn't see it for some reason.
Can I ask a question?
Sure, go for it.
Okay, so the written homework that from, I think it was last week, I think it was homework 7. So I didn't do it. Like, whoops, and like my bad. But I just don't like know how to do a lot of these. And okay, so like for can I like share my screen if you don't want to like pull it up?
Yeah, please go for it.
Okay, fantastic. Okay. So yeah, this is the deal. Oh wait, whoops, never mind. Hold on. All right, so for number one, like I was confused. I just wanted to like make sure that I'm like super clear on this. But the second partial sum, so A0 and A1 and A2, is that just is that like the whole like do you have to find the series for it and then like
Yeah, when it says the second partial sum, it's a little confusing the way they wrote it, because they wrote it almost as if it's just going to be a normal sequence, but it's actually like a degree 2 polynomial.
okay, good, because that's what I thought kind of, but like so you would just you like find your derivatives and you plug it into like the wait. Oh wait, did I do that right? I don't know if I did this right. Okay, so I like you're supposed to find the derivatives of f to the n of 5, right? Like you find, I guess, 3 derivatives of that, and then
Yeah, well,
like do you plug it into like you do like the second one would be like whatever that derivative is, and then x minus 5, I guess.
yeah. So you only need you need 0th order derivative 1 and 2.
Okay.
So you're using n is equal to 0, 1, and 2 in that formula for your derivative. So that'll give you the part of the coefficients. You do have to remember to divide by another factor of n factorial.
Yeah. Okay, good.
That
Because
times
I thought that was right. I just wanted to like make sure that that was like okay. And then when you find the Taylor series for it, would the Taylor series for this one be 2/5 -1 to the n, and then 5 minus 5, like all that over 5 to the n?
Sorry, say that again.
Would the Taylor series be like the sigma thing? 2/5 times -1 to the n times x minus 5/5 to the n. Like
Sounds
all
right.
of it to the n.
Yep.
Okay, good. So to find what values of x it converges for, is that when you do the root the ratio test and then take the limit of it?
Yep.
Okay, good. So then what does it mean? What does f of x equal? Like what does that mean, like find the sum or like oh
Find
they
the
want us the original equation. Yeah, how do you know what the original equation would be?
Yeah, so this one you're kind of going backwards. So we've done a lot of problems where given a function, you can come up with a power series or a Taylor series for it. This
Mhm.
one we're working backwards. We're kind of given information about the Taylor series. You got to work backwards to deduce the function. So your Taylor series, you said 2/5. You've got a -1 to the n, and then you said x minus 5/5 all to the n. I think is what you said you got. I think that's right.
Okay, wait, let me take yeah, that's exactly what I got.
And so what we want to do is find the closed form expression for f of x, find the Cartesian equation for f of x. And so you have to kind of like reverse engineer and finagle this into a format that looks somewhat recognizable. Let's pull out the 2/5.
Okay, so then that looks like geometric, right?
Yeah, exactly.
Okay, so then fine, so then what's the actual equation for it would be, I know that like the A would be 2/5 and the R would be this x minus 5/5. Oh wait, I see what you did there. Okay. Yeah. So how do you get that into like an actual f of x equation?
Here, let's change the variable.
Oh, really? Whoops, that's it.
So this is
Okay.
your y. You just stick that in for y. As long as the radius of convergence works out. So you should have found the radius of convergence should have been 5 for x.
Oh no, I stopped after part B. Like I really just decided not to do this one.
No.
Terribly sorry.
Yeah, so because of that 5 to the n in the denominator, you should find a radius of convergence of 5, which is going to be consistent with the radius of convergence here, right? This y has to be between -1 to 1, which means that everything in here has to be between -1 to 1, which means your x, the radius will be 5, and so your x values should be between 0 and 10.
Okay, good. Okay, that's fantastic. All right. Looking at the oh wait, I think that you guys did this other one. Okay, wait. Sorry, I'm gonna share my screen again. Okay, so to find a use a power series to find the area under the graph of f of x, e to the negative x squared. Okay, so you have to use how did we use like a power series for that? I know that e to the x or something is like a known power series, right? But
Yep.
Can we just put in like negative like x squared instead of x in that thing and it's fine?
Yep.
Oh my god. Okay, well that's pretty cool. Okay, so you have that and then find the area. Okay, so how the area of it would just be like you take the integral of it?
Let's see. Find the area under the graph between -1 to 1 with an error no greater than 10 to the -4th. Yeah, this one's a little tricky. You're going to want to you'll end up using an easier error bound, though. You don't have to use the Taylor's approximation error bound.
Gotcha.
Which is nice enough. You can actually use the alternating series at your error bound. The alternating series error bound is a bit more simple.
Yeah. Okay. So let me stop sharing again.
What was the error?
The error was 10 to the -4. Actually, okay, I kind of get how to do like the error bounds and stuff. So I don't want to like take up your time with that because like I think I didn't know how to get it. I wanted to like make sure you could put it in a power series like that.
Yeah. Do the power series, you'll have this guy from whatever power series you have.
Okay.
Integrate term by term and then actually evaluate it. So you'll plug in, after you integrate, plug in the ones for the x's, and you should be able to see what type of series you have after that.
Because then you would have something, you would have n left over, right? If you did like the Taylor's estimation theorem, you would have like some value of n left, right?
What do you mean by some value of n?
Like when you take the integral of this, like the integral is going to be like, you're not going to have any more x's. So, but you're still going to have like n's in the
Right. So you'll
in your
you'll
answer. So then do you just like set that as like less than 10 to the negative fourth and then like isolate n?
kind of. So you'll integrate.
Oh wait, because it's never mind, it's the Taylor's one. So you have to maximize the things. Okay.
So you're going to
Whoops.
want to look, you won't have Taylor's remainder theorem in this one since you'll have your minus 1 to 1. So you'll integrate and you'll end up with a sum of whatever your functions are here. It'll be some sort of series of x. Then you're going to evaluate that from minus 1 to 1. When you evaluate your ones, it'll get rid of your x's. So then it'll just look like some series. And then after you evaluate it at your minus ones, you may want to try to combine those into one single series. And then from whatever this looks like, you want to use potentially the alternating series to actually find, don't go all the way to infinity, but find an n so that the sum is within the margin of error. Does that make sense, or do you want me to explain it?
Yeah, no, that does make sense, but how would you like what would be your next step after that? Like if it's so for this one, you could have used like the alternating series estimation theorem, right?
That's probably what's going to come out. Yeah.
Okay, then that would make sense. Could you use like if this was like if it looked different, could you use the Taylor's estimation theorem, or is this like
Yeah.
is this still a okay?
You might have to. So it actually is going to depend on what it looks like after the integral.
Got it.
And then we're really going to look at like the error of that on the interval of minus 1 to 1.
Okay. Got it. That sounds pretty good. All right. Well, let me make sure that I don't have any more questions on this thing.
Yeah. I mean, if you want to work that out and work through it, let me know if you get stuck anywhere, and then we can kind of go back and maybe be a little more specific.
Okay. Yeah. Because I feel like this is probably something that it would be helpful to like know how to do on the exam, right?
Yeah. I mean, you should know how to
Sort
do
of.
Taylor series, know how to do manipulations of Taylor series.
Okay. So
all the error bounds.
okay, gotcha. So the like the examples where you had numbers written like all across the page and it was like one line and another line, and it's like power series and you're doing like the long division or something like that. That's not going to be important. Because you said something like that in class, and I just want to make sure that I don't need to like.
That's still, as of yesterday, it was not terribly important.
Because I mean, like I could spend the time to like figure it out, but I really just don't like. Just really don't want to like at all.
No one wants to.
Yeah, that's what I was. Okay, I feel like they wouldn't put it on the exam.
When we need to, but
that must be a bitch to grade. Like, oh god.
look. Yeah. It's not terribly important. You should know how to do all the basic manipulations of power series and Taylor series, okay. Multiplying by constants, manipulating indices if you need to, integrating, deriving.
Okay, so what's the deal with integrating and deriving them? Like what was the, I remember doing it, but I don't really remember like what it meant, like why it was so important.
So think of like the most important ones were the ones we started with were like arctan and natural log, because the derivative of these guys looks very similar to the geometric series.
Oh, gotcha. Okay, so then you're saying that okay, so if you're trying to find a power series representation for arctan, then you would just want to take, you'd take the integral of like, would you take the integral of this 1 over 1 plus x squared if it was in the form of the, like the form we have for it?
Yeah.
Okay, and then I guess that does make sense that those are equal. Okay.
So you could simplify that a little bit if you want, and then integrate that side and integrate that side. And so we get the formula for arctan by integrating that power series.
Okay, and then when you're integrating it with respect to x, right?
Yep.
Okay, good. See, it seems like it would be hard, but then you're like, you only have to worry about the x's, like the n's don't matter. So that makes it better, I guess. Okay, and then I'm gonna use Taylor polynomials. Okay, and then the position ones, those are pretty much just like parametric equations, right?
Yep.
Where it's like position. Okay. All right, this is probably fine. Thank you so much.
Welcome.
Yeah, I finished the written homework, so thank you.
Good.
So, and thank you for being a good professor. I actually enjoyed this class. It was rushed, but you made it
Dude, it's
manageable.
always
So.
summer is always just so rushed for everyone.
No, I heard you. You were ranting about like the summer course. I'm like, yeah, I feel you.
Okay, yeah.
I don't
that was
ever want to.
definitely funny.
I don't ever want to do a summer course again. It's not.
No,
worth it.
like I tell, like Calc 1 is even just as bad, just because like a lot of students will jump into Calc 1, or even worse, we'll get high school students. And like a lot of high school students, unfortunately, our high school system has degraded a bit in terms of like, we kind of shuttle students through high school because we only have publicly funded, you know? And so since we're not paying our teachers well enough and we don't have the funding to really pay for students to be in school, the high school standards have been decreasing quite significantly over the years, which is bad because then they come to college kind of expecting the same thing, or even worse, they graduate their senior year of high school, then take a summer course in summer math. And not only is it collegiate math, which is way harder and way faster than high school math, but then it's during the summer, so it's even faster than that. And it's just, it turns out really bad for a lot of them. They can get kind of snotty too.
I can imagine that sucks. Also, sorry that people like bitch at you in class sometimes. Like, I get it, summer's so fresh.